In this video, I want to talk to you about continuous probability distributions. Back when we were talking about discrete distributions, the value of x jumped from one value to the x. It went from 0 to 1 to 2 to 3, etc. Continuous distributions are different. They can be any value. I think back in your notes somewhere it says any value specified over a range of values. So think about my travel time to USF. My best travel time is around 20 minutes. The longest is maybe 45 minutes. Anywhere in between there's fair game. Any value of x. It doesn't have to jump from 22 to 23 minutes. It could be 22 and a half. It could be 22 and 3/4. And so that's the definition of a continuous random variable. And so what we're going to be talking about with probability distributions is they're just going to be represented by a curve over the values of the random variable. And so I'm going to come here and grab a pen and I'll say, here are values of x. You can think about, I don't usually typically have an axis here, but you can think about probabilities on this axis. So I'll actually kind of draw it in here. Let's say p of x. The probabilities of x. Obviously, where you have higher parts of the distribution, the peak, if you will, of the curve, those are the values that occur more often. So in my travel time case, probably between 24 and say 30 minutes. That's the majority of my drive times. Occasionally it's a little less than 24, occasionally it's more than 30, and maybe it looks like this skewed right distribution. So there's a couple of ideas that we want to talk about. First is the total area under the curve is 1. Back with the discretes, we said that the probabilities all had to be between 0 and 1, and that we summed them up. They summed to 1. This is that second one. When you apply it to curves, rather than the sum of the probabilities is 1, the total area is 1. The second rule, so to speak, is if I come out here to a value of c, and maybe c is, what's the probability at 40 minutes? The probability it takes me exactly 40 minutes to drive home is 0. It's a weird idea, I know. The probability it takes me exactly 40 minutes to drive home is 0. The probability it takes me exactly 22 minutes to drive home, 26 minutes. Any value of c, the probability equal to probabilities won't make sense with continuous distributions. So I'm going to write this. And this is the kind of thing that we start looking at. So I'm going to come in here and I'm going to put a, maybe a is 25 minutes. And b over here is 27 minutes. The probability between a and b, not including the endpoints, is equal to the probability when you do include the endpoints. And this is a product of the second one here. We're going to be interested in probability, shaded regions, the probability greater than c, the probability less than c, the probability between a and b. It's not an easy idea to think through. And I'll give you a quick kind of tutorial with the probabilities. I remember this is the way it was explained to me. If I want to know the probability between A and B when I'm looking at a curve, that's tough. I remember doing stuff like this back in probably, a calculus class? And some of you guys are starting to get a little sick. Sorry about that. And I'd say if I want the probability between A and B, I would take the function and do some integration. And I'd say that's the probability between A and B. Now, before you guys get too freaked out, I'm going to go and get the pretty purple here. And I'm just going to do this. We're not going to do any of that, so relax. Okay, you've seen the amount of calculations I've asked you to do. We're not going to do stuff like that. But I do want to kind of talk you through it. I remember I had a calculus teacher who said, well, integrating or figuring out probability with a curve is tough, but think about just a rectangle here. When you sit in the classroom, there's a screen at the front of the classroom. Think about trying to figure out the area of that screen. You would do a height times a width. And so he said, it was a he at the time, he said, think about the rectangle there between A and B. You could figure out, we could probably figure out the probability here at the peak of the rectangle and be able to do the math. And he said, obviously, the part that falls outside the curve there, above the curve, is too much. He said, well, rather than think of one rectangle, let's see if we can split it in half. See if I can do this with the mouse. Not too bad. And think about two rectangles. And let's get rid of this piece here. Right, so now I got two rectangles, and you could say, well, I could figure out what's between A and B. For instance, if this is 24 and this is 26, 25, it'd be in the middle. So it'd be easy enough to do that. We could figure out two rectangles. And while the area is still bigger, because it includes those two little almost triangular spaces, I'm doing better than looking at one rectangle. And so he said, well, do it again. Split it in half. Look at 4 rectangles instead of 2, and then 8, and then 16. And so he said, really area, or area underneath the curve is a whole bunch of rectangles, figuring out areas of rectangles and adding them up. And if you think about that, when you think about the area of a rectangle, now let's go back to the single point over here. What's the probability? Area is probability. If you're looking at a single point, sure, there's a height here. I could really figure out where the curve is and what the height is there, but there's no width. There's no width to a box if you're talking about a single point. And so he was trying to help me understand why that might make sense, because on the surface that's weird, and I struggled with that, and a lot of times I find students do as well. And so the probability equal to C is 0, so we're going to be talking about probabilities between two values. Probability between A and B, the probability bigger than B, less than A, shaded regions. And so the bottom line of this discussion is equal signs don't matter. When you're working with continuous distributions, equal signs don't matter. Now, if I was back talking in terms of the discrete distributions like the binomial, the Poisson, which we didn't really look at all that much, equal signs matter a whole lot there. If I gather 20 people and I want to figure out the probability more than 10 have a tattoo, that's different than the probability at least 10 have a tattoo. Because there's a possibility exactly 10 could have a tattoo. So the equal signs were real important with the discrete distributions. They're not important at all when we move to the continuous probability distributions. All right, so that's some general idea. Total area under the curve is 1, equal signs don't matter. The normal distribution, this is the distribution that we're really going to be paying attention to. We say it's characterized, maybe a better word, described by mu, population mean, and sigma, a population standard deviation. The mean is, as we've seen earlier in the semester, it's the center of the distribution. The standard deviation is the spread, or a measure of the variation. And so when I go to put them on a number line, I might draw a curve here and say that's mu1. Terrible looking mu, sorry about that. That's the mean of the first distribution. Now, maybe these are your test scores. Maybe these are exam 1 scores, and I say that it's about a normal distribution. It's centered at mu1. Maybe it's centered at, I'll just make up a number, 75%. I'm actually making this video before I've looked at your exam scores. But let's say it's 75%. And let's say I decide, just because there's some quirk of nature, I decide I'm going to give everybody 10 points. What would happen to this curve? If I just added 10 points to everybody's grade, wouldn't it just shift up the number line? Wouldn't everything just kind of slide? The mean would be bigger, but the standard deviation would be the same. Okay, that's how the mean works in a distribution. It centers it. It gives me the location on the number line. And whenever I draw a number line, you think smaller numbers to the left, bigger numbers to the right. Okay, well, what I want to do is I want to draw a second curve, but not just increase the mean. I want to increase the value of the standard deviation as well. And so what I'm going to do is put a second curve on the line. Now, when I increase the mean, it's going to slide to the right, the center. When I increase the standard deviation, the spread is going to get bigger. Remember, increasing the standard deviation means the variation will get bigger. And when the variation gets bigger, because the area under both these curves has to be 1, if the spread gets bigger, if it gets wider, it's got to get shorter. So if I've drawn these curves correctly, they both have an area of 1. The first one has a smaller standard deviation. The second one has a bigger standard deviation. Now, because there's any value for mu, can be positive or negative, sigma has to be a positive number with the way it's calculated, but there's infinitely many combinations of mu and sigma. What I want to do with this first idea, the first set of videos, is to talk about a specific. I'm going to look at one of these infinitely many distributions. It's called the standard normal distribution. And this little picture I've drawn here, boy, it's really small. I can barely see it myself on my screen. This is the letter Z. It's called the Z distribution. This is a value of Z. And the mean of the standard normal distribution is 0. Standard deviation is 1. So this is a special normal curve. It's called the standard normal or the Z distribution. And when we use a Z symbol, it's going to be related to this distribution. Now, I'm going to talk about this specific value right here as a specific value of Z. I'm going to call it Z0, and I'm going to say it's that value right there. 0 is always going to be the value in the middle. Okay, so let's look at it that way. The next step is to try to figure out how we're going to find probabilities in this distribution, because we don't want any part of that integration that we talked about earlier. There are a couple different normal tables that are out there. They all deal with the standard normal distribution, so that's a natural place to begin. The table that we're going to work with this semester is called a cumulative table, and the table gives the probability z is less than some specified value z naught. And so as I look at this table, the gray shaded probability is the probability below the z-score you see listed in the table right here. The z-score in this table would be a negative number. As the z-score becomes a positive number, that shaded region is just going to grow. And so the smallest cumulative probability you're ever going to see in a table is 0. And while it won't actually be 0, it'll grow from 0 up through, when the whole curve is shaded, as the z-score moves to the right, it'll grow to a z-value of 1. Now, as we're going to see this semester, working with the standard normal distribution, or the z-distribution, is the key to unlocking all normal curves. And so typically we start with the z-distribution. There are infinitely many normal curves, as we've learned in this particular discussion. Only one of them is a standard normal, and yet that holds the key. That's the key to solving all those other normal distributions, and those are some things that we're going to get into in the next video. So next video, let's take a look at the standard normal distribution. So take a look at that cumulative table, and then we'll go on from there. So long.